Okay, so before we wait for those remaining people to come in these around 5 to 10 minutes, I want to have a quick question for you first, because Professor Skiena, he is currently visiting here for 1 year, and then he'll be back this June, and that means in the coming semesters, if we are still going to have this course, there is a possibility that I'll be the instructor instead of the TA. So I'd like to know what kind of things do you most like to learn from such a course? Algorithm? Well, that's a big topic. More difficult algorithms, I see. And you?
I mostly just took it for to get a lot of programming experience, just to write a lot of code and write a lot of programs.
And your? Mostly about algorithms. So, what do you think will be the main difference between this course and 271, the computer algorithms course? I myself also think in this year's 3.0, maybe some of the topics covered might not be so hard, but I don't know. Okay, so now we have 5 people here who can try to start. So today we are going to have a short discussion about the problems we've assigned on Monday. So we have 4 problems here, and so how many people are now trying to solve these problems in the past 2 days? Wow. Okay. Good. So 4 problems, and I try to solve them. In my opinion, the easiest should be the Bermuda Triangle, and then maybe robbery, and then the motorcycle, and star might be the hardest. I'm sorry that I might have underestimated the difficulty level of star a bit on Monday. I had thought it was an easy problem at the very beginning, but now I find it a little bit hard. And to be frank, I have solved it, but I have not found an easy way to explain my approach.
What algorithm?
I've solved it using dynamic programming, but based on bits. Yeah. It's okay, but I'm not so sure Skiena have dealt with such things. So so first about the Bermuda Triangle. The Bermuda Triangle might be the problem. So we have the equilateral triangles with edges equal to 1 meters, and houses are built at the circumcenters of the triangular fields, and then we need to find the shortest path between 2 of the houses. So it's easy to see. In order to calculate the shortest path, we only need to calculate the the distance between the Cartesian coordinate of these two houses. So basically, there are 3 steps for us to do before we need to code. The first thing is to convert the house number to the triangular coordinates. And then we need to convert the triangular coordinates to Cartesian coordinates. And then we need to calculate the distance between 2 points. Okay, we can forget about step 3, and then we can focus on 1 and 2. First, about step 1. Step 1 is to convert the house number to triangular coordinate system. So if we would like to, say, map 0 to 0, 1, and 2 to 0, 2, 3 to 1, 2. So, given a house ID n, what is the x and y of it in a triangular coordinate? Okay. These are just some mathematical tricks. First, we can observe that on each of the lines, the largest number would be 0, 3, and 8. And this line should be 15. It's easy to see by adding 1 to each one of them. We can get 1, 4, 9, 16, all squares. So it means for a line x, the largest number at line x would be x squared minus 1. So to find this should be 1 instead of this. Y squared minus 1. That means yn would satisfy yn squared minus 1 should be larger than or equal to n. And then yn should be larger than or equal to n plus 1. And get its square root. Okay, this is yn. So after we have yn, now we would like to know what xn is. To solve this, we first try to map 0 yn to an ID. And then by calculating the difference between n and ID, we can have xn. Okay? So it's also easy to see. Here we have 0, 2, 6, and 12. So 0, 2, 6, and 12. 0 is 1 times 0. 2 is 2 times 1. 3 is 3 times 2. And 12 is 4 times 3. Therefore, we can guess this should be yn multiplied yn minus 1. So calculating the differences between these two, we can get xn. Okay, now we can successfully convert an ID1, a house number n to its triangular coordinate. And the next question is how we convert from a triangular coordinate to its corresponding Cartesian coordinate. This part might be a little bit complex. We first we can see so each house is now built at the circumcenter of the triangular fields, and by definition of the circumcenter, we know these three paths should be equal to each other. And then we know this should be a 30-degree angle, since this is an equilateral triangle. And then here should be 1/2. And by simple calculation, we know this is square root of 3/3n. This is square root of 3/6. So how do we calculate? First, how do we calculate the x-coordinate? That is to say, given a we know it can be represented as -2, 3 being a triangular coordinate. How do we calculate? First, how do we calculate its x-coordinate in the Cartesian system? It is easy to see. It's easy to prove this should be one half, since it's the same as here. And this is also 1/2. So by translating from a triangular coordinate to its Cartesian coordinate, we can simply divide this by 2, and we can get the x-coordinate. For the y-coordinate, it will be a little bit harder. First, we know that the height from here to here should be y minus 1 times the height of the triangle. Since we have already passed y minus 1 levels here. And then it's easy to see the height of a triangle is square root 3/2. So the y-coordinate can be translated as yn minus 1 multiplies square root of 3/2. And then plus something. So what this something is about? We can see this something is either this part or this part. Notice that these two parts are not on the same height. Because if the triangle is upside down, then the distance from this edge to its circumcenter would be square root of 3 over 6, as we had calculated here. So if we are calculating the y-coordinate of house 5, we should plus square root of 3 over 6. But instead, if we are calculating the y-coordinate of house 4, we should be adding square root of 3 over 3. So the rest is that we only need to determine whether a triangle is upside down. And then we can calculate the y-coordinate, and then everything is done. So this problem does not involve any mathematical skills, but I don't know, any algorithmic skills, but it needs a little bit calculation. And as long as you get these translation formulas, I think it's done. So step 1, step 2, step 3. Step 3, if you tell me you don't know how to calculate distance between panels into a series. The code sketch is quite simple, and the full code is also quite simple. And I've now demonstrated it can be solved on the programming judge. Now, robbery. Robbery, we've already said, the problem, robbery goes something like this. We have a rectangular grid, and our goal is to find out where the robber was at any given time. And the information we know is that the robber isn't at rectangle Ri at time Ti, and we would like to know whether we can know the specific location of the robber at some time point Ti. So the information we have is robber is not at some rectangular Ri at some point Ti. So the key insight in this problem is, how are we going to propagate the information we have from one time point Ti to its consecutive or adjacent time points Ti plus 1 or Ti minus 1? One example we can have is, if we know the robber is not at this R at time T, then we can guess let me see. Oh no. Let me see. This one. If the robber is not, if we have some knowledge of a point xy where the robber is not at xy nor at its adjacent grid at time ti. Then we can know at ti plus 1 then we can know at ti plus 1 it cannot be at point xy. Since in order for the robber to be at xy at ti plus 1, it must be either at xy at ti and then stop to be staying at xy at ti plus 1. Or it must be at one of its adjacent grid and then move to xy ti plus 1. So our key insight is to pass this information from one time stamp to another. And the code sketch here is something like this. If we find at time point t, at time point t1, so the robber is not at is not at any of the 4 adjacent grids of xy, and it is not at xy at time t. And then we can know it's not at time. It is not at xy at time t2. So how we propagate this information? We can propagate first from t minus 1 to t, and then from t plus 1 back to t. It's a forward, backward. And by doing such an iteration in both two directions, we can ensure we can propagate all the information we need, and then we can simply calculate whether we can know. So the code here is just the pre-processing part, and here is the information propagation part. This is just calculating whether we can know the exact location of the robber, and then everything is okay. I find it a little bit difficult to categorize what kind of algorithm this problem is, but I do not think it's quite hard. So next is the monocycle. For monocycle, our goal is to find the shortest path between S and T. And we have some squares blocked here, so we cannot move into these blocks. And in each second, we either turn 90 degrees from left or right, or we move forward to the next grid. And the number of cells the cyclist has passed from S to T must be divisible by 5. This is to ensure the constraint that the cyclist must have the green part touching the ground at S, and then having the green part touching the ground at T. So since we have 5 colors, and then by by moving along 5 blocks, we can have an exact round. And then from S to T, the cells it has passed should be divisible by 5. And from S, the cyclist starts with facing north. So since we are going to find some shortest passing, our first idea is to use some shortest path algorithm to solve this approach. And the next point is that notice here we mentioned in each second. It means the weight between the edges in the state graph will only be unit weight. Then we can try to use some breadth-first search algorithm to solve this. So if we use breadth-first search, how do we represent states in the graph or states in the cube? We have learned breadth-first search before, right? Okay. So to represent the states, one might first think to use x, y. But clearly it's not enough, since by using x, y, we will not be able to represent what color is currently touching the ground. So we need another part, C. And after we have C, it's also easy for us to think. We also need another part to represent which direction the cyclist is currently facing at, and that is D. So if we have X, Y, C means color and the direction, can we represent a state that the cyclist currently is at? Here we have X and Y. Turn 90 degrees, we can handle it by T, also by D. And here we can also handle this forward thing by D. And this we can handle it by C. Seems okay. So for input constraint, so are we able to represent this state space? X is 25, Y is 25, C is 5, and D is 4. Multiply all these things together, we get a very small number. So it's easy for us to represent all these states in the whole cube. Okay, so this is how I do it. And for the BFS routine, it's actually simple. So we know a pseudocode for a BFS routine is something like this. So state S equals to start state, and we need to include S, and then while not Q empty. We first try to EQ something here, and then and here we need to use a hash table to mark this, and then we need to try all the possible 3 actions we can do at each step. The first is we can try to turn right. And the second is we can turn left. And the third is we can move forward. And if at one time we found that the head node at the Q is equal to T, and then we can have the answer. Otherwise, we just output the destination kind of switch. So this is the BFS part, and I think it would not be hard for you to write these. So after the moment cycle, we enter the most difficult problem, in my opinion, of this section. Anybody here have tried to solve this problem? Okay, so how do you? Yeah. Okay, that programming. And you? Search. Okay. I'm always thinking whether there are some easy solutions, because I myself also use dynamic programming, but I think it's a little bit hard. And I see in we can pass the problem by search, but there are some programs you can pass in relatively short time. I do not know whether it's possible for some simple calculation methods to work. Okay, so can you try to describe both of your two algorithms in front of the class?
In this problem, what we know is from each direction, we know the maximum value of each line, and we need to find out the largest possible sum of all the digits on this board and the minimum sum of digits on this board. And I believe that it is very easy to find out the maximum sum, because for each there are 48 digits on this board totally. And if I I saw, for example, I saw from 8, the maximum number is 5, and this implies that every digit on this line is at most 5. So it's maximum. I said it's 5 first. Then if I watch from F, for example, F is this line, and its maximum is 1. So because these 2 digits is at most 1, 2, so I change the maximum is 1. So every time I get the minimum value of this digits, and then I sum up all the digits, and I get the maximum answer. And this is the way to calculate the largest possible sum, and how to calculate the smallest sum. First of all, I have to say that if we find out a solution which has the smallest sum, and at most 12 of them of the digits, at most 12 of the digits is non-zero. What's more, I started searching the value from the largest 9 to the smallest 1. For example, in this sample input, we saw from the D this line, and we know that there is on this line there is a 9, must at least 1 9, and we saw from this this is G, right? On this line, that is at least 192, and from I is same. So I make a very simple algorithm to, for example, I want to find out the minimum number of 9. So from by searching, the only solution is only put a 9 on this digit, and I finish assign 9s to this ball, and this is so the next step is to assign 8 to this ball, and then assign 7 to this ball, and the way to assign the values is to find the minimum number of 7 or 8 or other else to meet the requirement that every line at least has 1 9 or 7. So this is the way for me to perform the research.
Okay, good. So when I was trying to, at the very beginning, I also thought about the searching approach. But I was thinking, instead of searching, can we actually try to determine each of the value without backtracking? Say, if we process all of these digits from in non-increasing order, then we can know 9 should be here. And then we can see we have 8. We have 2 8s. So the best for us to do is to ensure these two 8s should be the same. So to ensure these two 8s are the same, we can see this is C and this is J. And then for C and J, we can put it here. And then we have 7. We have only one on 9B. So here, in order to put it on 9B, we should.
We must have a solution because every digit can be seen only from 3 directions.
Yeah. I think if we can we simply use some kind of greedy methods up to that to determine all of these spaces. Is it possible? Say if we have B here and we know so in this line it seems we need to yeah. Have you submitted your program to
Yes. I just accepted on UVA and my name is CHEN.
Oh, I see. This is not the. Yeah, Firefox.
There is a Firefox here.
There is a Firefox here. Oh. Be round columns and contest volumes or program calendars. Chapter 12. Airline, star here. I'm not so familiar with the new system of EDA. Do they still provide statistics?
Yeah, and the ranking.
I see.
I'm not sure I'm on the first. I can log in.
Okay.
Because many of them is
Okay, I'm just wondering how long your search program can pass.
okay.
It's okay. Okay, so
But what my step
here.
is this text. Huh? What?
Maybe it's not this ID. I don't know.
What's the idea of this bubble?
Let me see.
Okay, it doesn't.
10159. Yeah, it's okay. Okay, so Qifeng talked about searching solution, and maybe you can tell us more about your dynamic programming algorithm. Try to. Okay.
It's fine to remember it.
Try to write down something first, and as time goes by, then remember more and more.
I think I should watch it out of my program first.
Okay.
My program is a little bit dirty.
It's okay. My program usually is dirtier than yours.
Maybe I should write something.
Okay. So before he recovers what he's coded about, we can first have a talk about what we had last week is for 2 world finals problems. How many of the students here are currently involved in the ACMI BCE programming team? You 3? You 4? I see. So, you 3, I see. Last time we had talked about problem A, And this time we go to problem B, which is another easy problem in this year's world final. Problem B, the description of problem B seems a little bit complicated, but it still is very simple. The basic idea about what problem B is we are dealing with logical circuit this time, and we have AND gates, OR gates, exclusive OR gates, and block gates. So from these gates we can compose all kinds of complicated logical circuits, but in real-world situations, real gates sometimes fail. And we limit the cases where real gates fail to one of the three ways. One is the real gate which had failed will always invert the correct output, or it will always yield 0, or it will always yield 1. And in the circuits for this problem, at most one gate will fail. This is a very important constraint. So we are writing a program to analyze the circuit and a number of observations of its input and output to see if the circuit is performing correctly or incorrectly. We have at most n inputs, at most 8 inputs, at most 19 gates, and at most 19 outputs. And then we have B numbers of observations, but we do not have a constraint on B. But it's easy to see B will at most be 2 raised to the power of 8, since no two observations have the same input values. Okay, so this is a rather brute force algorithm, since in my opinion, algorithmic content is even much easier than problem 8. Since actually we do not need to handle anything, we just parse the input and then we test over all kinds of observations to see if it's correct. If all passed, and then we just write no faults detected. Otherwise, since we have 19 gates and at most 1 gate will fail, we only need to do a linear time guess over which gate has failed. And then after we are trying which gate has failed, we just try one of the 3 possibilities over why it has failed, whether it is inverting or it stuck at 0 or stuck at 1. If by assuming one gate GI is failing at case J, we can correctly explain the input and output correlations. Then we add a counter by 1. If after all of these evaluation processes, the counter is 1, then we say it's okay. Then we say yes, one of the gates has failed, and we can determine why it is failed. Otherwise, unable to totally classify the failure. So problem B is also very easy, and normally in this year's world final, this problem would be the second problem to be passed after problem A. The next problem I'd like to talk about would be problem F. Problem F involves some knowledge in chapter 14, but I'll not talk about the algorithms of that part, and I'll just tell you that part can be easily calculated. So the problem of this is there are some points here, and their situation is that they assume these points are grass, and they're not these grass. Okay, so they want to build fences across these, around these grass, in order to ensure that deer would not be able to eat them. So a more real constraint is that every fence must lie at least a minimum distance from each sapling. Okay, so this is called a margin. So that means if I want to build a fence around this one, and if I ensure the margin to be 2, I should build an exact circle. So if I build a margin, a fence around these 2 points, then I should build something like this. So it's normal for him to want to minimize the total length of fencing used. Okay, this is the objective we have. So our job is to write a program that computes the minimum length of fencing that is required to enclose and protect the saplings. And we can see, we can either build this way or build that way. The input constraint is we have at most line points, and the margin would be less than 200. Okay, so how do we try to solve this problem? The first problem is if we have a number of points on a Computational plane, and we want to use a polygon to enclose it, like this. How do we determine the length and how this polygon should be constructed? This is called a convex column. And a detailed algorithm can be found in chapter 14, section 1. So I will omit this part and just tell you, you will soon learn how to calculate it. Okay? So now we have a constraint is we want to have a margin to enclose these points. If we have a margin, how do we, and we first ensure we can only use only one fence instead of several fences to solve this problem. How are we going to do it? It's more like a mathematical trick, since it's easy to prove. If we want to ensure a margin M outside of this convex hull, the total length we need now is the length of the convex hull of this set of points plus 2 pi m. In other words, we just calculate the convex hull plus the circumference of a circle with its radius as m. I think it's easy to prove this since we are going a round angle here. And in each round angle, we are extending it to n. And then it's okay. So now we have this part. Now how do we determine the minimum length solution? To find the minimum length solution, we should use some kind of dynamic programming methods. We should know that for a set Fs, the optimal solution might not be this one, but might be Ft plus Fs minus T. Here, if we order this as 1, 2, and 3, the optimal solution is not F1, 2, 3 itself, but it should be F1, 2 plus F3. This kind of dynamic programming on sets is usually implemented using bit vectors as you will see. Okay, so it's easy to see we can implement a dynamic programming method in this approach, and the complexity. It's easy to observe. N is 9. N is 9 means there are at most 2 raised to the power of n number of sets, which is 500. Yep. And then by enumerating all its possible subsets, still it's at most 500. Yep. And by multiplying this together, reaches around, say, it means at least we can have an affordable solution that can pass the time limit. And in practice, when we see the input constraint is very small, we can always try to think whether we can have a search solution or whether we can have a dynamic programming solution based on sets. So that means as long as we use knowledge taught in this course, and if we can master them well, it seems we can pass 3 problems in this year's course. Finals, which would not be a bad result, since the team from University of Hong Kong only passed 2. So, okay, so now it's time for you to talk about your dynamic programming solution.
Actually, we only need to solve the minimum part as a maximum is easy to find. My algorithm to solve it is to put the number 1 by 1. I number the triangle 1, 2, 3, 4, 5, 6, 7, and in this way. And my dynamic programming is something like this.
J is for
Before you talk about your state transition function or equation, you should first tell me what Fij is.
I'm
Okay.
Here I means that I finished putting putting number in the first
First I steps.
size I cell. Okay. And J is how many these rows is already satisfied.
How many what?
How many these rows?
I see. That's to say how many
Yeah.
maximum constraints are already
Yeah.
satisfied. I see. So the total number of states should be 48 multiplied 576. Y should be I see.
And this is the of course this is the minimum result.
Yeah.
And here, and I think it's obvious. I can either put a zero, or put the maximum number inside the constraint.
Maximum number inside the constraint means
For example, for this cell, is constraint 3.
I think it should be the minimum over the maximum.
The maximum inside. There are 3 constraints in this cell.
Yeah.
So it will has a integration line.
Yeah. Yeah.
Something like this. And I can either put 0 or this number.
You mean yeah.
And I have to update this J, and J is equal to J which is satisfied.
I think should be J equals to J prime.
Sorry.
Yeah.
Sorry. And which row is satisfied by putting this maximum number.
Okay. So our solution is more or less the same, but it's okay. So let me amplify his solution a bit because I'm sure not too many people will follow his words. By the way, one of the main reasons for me to dislike Skiena's work is his exercise most of the time is totally irrelevant to the topics he had taught. So, like this time, only this problem is related to grids, but yeah. Okay, so how are we going to use dynamic programming algorithms to solve this problem? Start. Okay, so let me first try to start. The first thing is that to use a dynamic programming algorithm, for me, I'll first ask myself what a state is, and whether this whether this state can both sufficiently represent the things we need. So here we have 48 cells. And we have 12 row constraints. Putting a number in a cell, the effect is that it would affect some row constraints. No, it would satisfy some row constraints. And in order for all of the 48 cells to have a minimum sum, our solution should be, if we will try to put the largest number. We should put A here instead of putting any other number here, since it's obvious that putting any number smaller than A would be a waste of time. So his state representation is Fij, where I ranges from 1 to 48, and J ranges from 0 to 2 raised to the power of 12 minus 1. I means we are actually trying to fill all 48 cells here. And J means we are trying to satisfy the 12 constraints. In order to use, the reason for us to use 2 raised to the power of 12 minus 1, which is this number, instead of 12, is that instead of simply counting the number, we need to record at each time what row constraints have been satisfied. Therefore, the initial condition should be F0, 0. And then for each Fij, we can either put a 0 into I, and then nothing will change. It should be Fi minus 1j, right? Or we should put the maximum allowed number at cell I, which should be Fi minus 1j prime plus a or max I. So the only question left for us to solve is, what is this j prime? Clearly, if we are putting a maximum number allowed at cell I, we are satisfying some row constraints. And to be as greedy as possible, we would hope such a constraints, if solved at this time, would have never been solved before. That means j prime would be j minus the constraints ai had satisfied. Okay, so we can have the j prime here. And then we have successfully defined what this recurrence equation is. To estimate the time complexity, it's easy to estimate the time complexity of a dynamic programming algorithm, since its time complexity is always state number multiplied transition cost. So it's easy to see state number is 48 multiplied 4,000, and transition cost is what? Why is why no? I see. Yeah. So it's 12. So multiplying all these together, we get. I'm not able to calculate this. Anyway, multiplying all these together, we get at around this number.
You only need to check.
That's why I assume it's a 1. But if you assume that the bit operation also take cost, you have to say it's 12. So it's okay. So this time complexity is well above the time, well below the time limit. So we can use dynamic programming to solve this problem. But still, I always believe that there should be a simple solution to this problem, but I don't know how. Okay, so time is more or less finished for today's course. And starting from next week, Skiena will be back. So you'd avoid. Yeah. So I think we are having only 1 week. Yeah. And I'm not so sure what the. Do we have a final test? No. We don't have a final. Okay, so see you next month. Or maybe it might not be I myself to see you next Monday, but someone would see you next Monday.